We present SHIELD, safety on humanoids via CBFs in expectation on learned dynamics. Robot learning has produced remarkably effective black box controllers. However, ensuring dynamic safety remains challenging. RL embeds constraints heuristically while model-based approaches require accurate dynamics model. SHIELD bridges the gap by learning the dynamics residual and enforcing safety with a stochastic discrete-time CBF formulation. The SHIELD framework sits on top of a complex controller as a modularized layer. A generative model learns the distribution of dynamics residual given a past trajectory of reduced order states and inputs. The tracking filter module corrects the commanded input to better match the reduced order model assumptions. The safety filter module then filters the corrected inputs given safety constraints. Note these modules can run alone if need be. We perform experiments both in the lab and in the outside world with the SHIELD framework running fully on board the Unitree G1. In these experiments, we use an A-star global planner to plan a path clear of obstacles, though not necessarily guaranteeing no collision due to the inaccurate dynamics model. We first present SHIELD under the single obstacle setting, with the built-in controller and our custom RL controller to test both validity and generalizability. We compare three methods, naively following the A-star path, filtering with a nominal CBF QP, and using our SHIELD framework. SHIELD is able to account for the inaccurate reduced order dynamics to guarantee safety on the left, and adapt its conservatism to the environment to produce more dynamic behavior on the right. Secondly, we present SHIELD under multi-obstacle settings. Similar behavior can be observed, with the nominal CBF not able to handle the dynamics residual on the left and colliding into one obstacle while SHIELD manages it with ease, and on the right, the nominal CBF is too conservative while SHIELD, being able to adapt its conservatism, only enforces safety heavily around the obstacle, thus produces far more dynamic trajectories. Lastly, we present SHIELD in action out in the wild, in unstructured environments. We test SHIELD both on pavement and in machinery workshops with a safety operator trying to steer the robot to collide with people. The robot is able to use SHIELD to avoid a variety of pedestrians, workers passing by and general obstacles in the scenes, further validating the effectiveness and generalizability of the framework.
Power of the force. Now slowly go towards it. Slowly. Step. Step. See? You're using the power of the force. Step.
In this work, we demonstrate that SHIELD achieves high-performance walking and robust safety constraint satisfaction under uncertainty on humanoid robots by combining a general-purpose RL locomotion controller with a robot-specific stochastic safety layer. Importantly, we want to emphasize that SHIELD can be added to an existing autonomy stack, wherein the dynamics of a nominal controller can be learned as the residual on a simplified model. Thank you.